We're going to talk about a integration technique. So far, we've just used the basic rules of integration, and we're really not going to change any rules. We're going to see a technique for being able to integrate more complicated things. And I've just started a problem. Actually, I've completed a problem here where we're asked to find the integral of x squared minus 1 in parentheses squared times a 2x. Find the integral of that with respect to x. And about the only tool we would have at this point is dealing with that x squared minus 1, the quantity squared. And so over here, I've just taken that and I've done that squaring operation. And then I just replaced it in the integrand there. And then I multiplied it all out, and I just had a polynomial. And so that's really, we can handle this without a great deal of fanfare. Now, the problem ends up being much more difficult if we're asked to integrate x squared minus 1, let's say to the 10th power, times 2x with respect to x. Now, that would be a real cumbersome job, because that power of 10 would take us a long time to multiply all that out, wouldn't it? Take us a long time. And you can imagine if it would have been a power of 20 or something, it'd be much worse even. So we're going to come back, and actually we're going to be able to do this fairly rapidly. But before we do, I want to remind you of a couple of things, okay, that are related to this. We do know how to integrate something so simple as the integral of x to a power. Okay, and just as a reminder, we do have a rule for that, and it says that we increase the exponent by 1, and we multiply by the reciprocal of that new exponent. And so we know that when we integrate something of this form, we get a look like that, don't we? Of course, this is true for any exponent except -1. Now, I also want to remind you that there's nothing really special about the variable x. We could have written the rule with another variable. See, we could have said the integral of the variable t to the nth power, but then we'd say with respect to t rather than with respect to x, because our variable is t. And then the rule would play out the same. It would still be 1 over the exponent increased by 1, but now instead of an x, we have a t to the power n plus 1. Plus our constant integration. Okay, again, the exponent can't be -1. Now, remember, it can be any variable, and this is really the one I'm after just to make a point. We could have a variable u. Okay, and so the rule would look like the integral of u to the nth power with respect to u, or du. And again, the rule would play out the same. The only difference is that our variable is u and not x and not t. So it would look like this. Now, this method of substitution really relies on this idea right here. And in fact, sometimes it's called U-substitution. See, sometimes it's called U-substitution. And here's the big picture. What we're trying to do is take integrals that look like this one right here and write it so that it says the integral of u to the 10th power instead of the integral of x squared minus 1 to the 10th power. And that is where the idea of substitution comes in. So let's work on this problem. Let me write it down formally, and here's what we're going to do, is we're going to find the integral, in this case, the integral of x squared minus 1 raised to the power 10 times 2x with respect to x. That's what we're going to find. Okay, so let me kind of get started. Let me rewrite the problem over here. The integral of x squared minus 10, x squared minus 1, I'm sorry about that, raised to the power 10, 2x dx. Okay, now that's how we're going to get started. But now what we're trying to do is create u to a power, and so it becomes real clear here. I apologize, that's so sloppy. What I want to do is replace that x squared minus 1 with a u. Because then it will read the integral, and instead of x squared minus 1, I'm putting a u. So it will read u to the 10th power. But then I have a 2x dx. Okay? Let's kind of separate what's going on here. So you see that it kind of looks like now, an integral of u to the power. Except we have this extra stuff, 2x dx. And see, when we're talking about the integral of u to the nth, we need a du, not a 2x dx. So we've got to get this, we've got to somehow do a replacement so that we get a du instead of this 2x dx. And here's the way we do that. We look over here at the substitution that we made. And it's, this could be like y is equal to, but it's u is equal to. And so what we do is we take the derivative of u with respect to x. See, that's just the derivative of x squared minus 1. The derivative of u with respect to x is just the derivative of x squared minus 1, which is a 2x. And then what we do is we multiply both sides of this equation with the denominator dx. I'm going to go through all the steps right here, but not normally do we write it this way. I mean, not normally do we do all these steps. I tell you what, for convenience purposes, I'm going to multiply the dx on the right side there in that fashion. And so we end up getting this dx cancel over here, and we have du is 2x dx. Now the significance is right here we have a 2x dx. And this allows us to replace 2x dx with a du. So we can do a further substitution and substitute du for 2x dx. Now, we know how to integrate u to the 10th with respect to u. What is that? Well, we increase the exponent by 1, so it's an exponent of 11 now. We have the factor, which is the reciprocal of that new exponent in front, and then, of course, plus our constant of integration. But to finish this, of course, we really need to put back the value of u. And remember, u is nothing more than x squared minus 1. So this becomes 1 over 11 times x squared minus 1 to the power 11 plus our constant of integration. Now, I challenge you to stop this video and calculate, to check, okay, by calculating the derivative of our answer. And I'm using the excuse that I'm out of room here, okay? Calculate the derivative of our answer and see that, in fact, you get x squared minus 1 raised to the 10th power times 2x. Remember, that's what it has to be equal to, and that's the big question. I challenge you to do that, but I guarantee you that you will find that that's true. So we have found this integral. And this kind of sets us up to things that we'll do in the future then. And it gives us an idea. Okay, let's go to the next page for our next problem. Okay, here's our second example. We're to find the indefinite integral, that is the integral of 8x times the quantity 4x squared plus 5 raised to the 6th power with respect to x. Now, again, let me remind you, we're looking to create an integral that looks like the integral of u to the power. And in this case, the big power that I see looks like a 6th power, doesn't it? So we're looking to create that form because we can integrate that form. And so that kind of gives us how we're going to start this problem, I believe. So let's rewrite it. The integral of 8x times 4x squared plus 5 raised to the power 6 with respect to x. And that kind of gives us a hint right away that u needs to be the 4x squared plus 5. Okay, that's what u needs to be. So when we look at that, then our integral becomes 8x, and in place of 4x squared plus 5, we have a u. So it's times a u to the 6th power and then a dx. Now, probably what we need to do next is we need to kind of gather together our things involving x and our things involving u in this integral. And of course, we can't really move the dx around because that has to be at the end. So I'll move the 8x and the u to the 6th, and it looks like this then. Okay, same integral, it's just kind of rearranged inside. Now, we're back to the same position that we were a moment ago. Now, remember, okay, I'm going to go through this again. Over here, we have u, and because of that, we can kind of somehow solve for du by taking the derivative of u with respect to x. And when we take the derivative of u, which is 4x squared plus 5, with respect to x, we get an 8x. And then when we multiply both sides by dx, then we end up with a du is equal to 8x dx. Now, what I'm suggesting to you, or what I'm going to tell you, that in the future, I'm going to skip that middle step. And I'm going to say, okay, here's what I know about du. Du will be the derivative of the right side times dx. See, that's the way I'm going to do that in the future. But nevertheless, in this case, I'm kind of lucky again. Here is my 8x dx that's appearing right here. And so I can replace 8x dx with a du, and it becomes the integral of u to the 6th du. And like I said, now we know that's what we're trying to get. Now we know how to integrate that. That will be 1/7 u to the 7th plus our constant of integration. And of course, then we go back and we replace that u with 4x squared plus 5. Okay? Plus our constant of integration. I'm formally going to check this one, just to show you that we, to the power 7, my bad. Don't forget that power 7 there. Okay, now, what we're going to do is we're going to take the derivative. Remember how we check. We check to see that the derivative of our answer is our original integrand. So we're going to check by taking the derivative of our answer here. Okay, and our answer, 1/7 times 4x squared plus 5 raised to the power 7 plus that constant. Now, here we have a situation where we would break that down to the derivative of the first term, which would be 1/7 times 4x squared plus 5 to the power 7, okay, plus the derivative of our second term. But our second term is just a constant, and so that derivative will end up being 0, won't it? That's a 0. Now, when we go over here to take the derivative of this complicated mess, well, we really have to use the general power rule, don't we? So the general power rule says, okay, we've got this constant 1/7, we'll bring down the exponent to 7, and we'll decrease the exponent by 1, won't we? So now, we brought that exponent down, but we decreased the exponent by 1. And then we also have to remember then that we multiply that with what's inside the parentheses, the derivative of what's inside the parentheses. So we've got to multiply with the derivative of 4x squared plus 5. And you can see it's all working out, can't you? The 1/7 times the 7 is going to be 1. And so we have a 4x squared plus 5 raised to the 6th power. And the derivative of 4x squared plus 5 is just an 8x. And with just a simple rearrangement, that's an 8x times 4x squared plus 5 raised to the power 6. And so we, in fact, do have our original integrand. And so it does check out okay. Now, in the future, I probably think it's a good idea for you to check these. I'm not going to particularly check all of them. But you know what you need to do now to make that check. Let's go to the next page for example 3. Okay, here we are in example 3. Find the indefinite integral, which is the integral of the quantity 3x plus 4 raised to the 12th power with respect to x. And I hope we're already developing the idea that we're kind of looking for a power in parentheses with a power on it, because what's in those parentheses is the substitution we're going to make for u. Now, things aren't going to work out quite as neatly in this problem, but we can still do it using this substitution. Here's what I mean. Here's our integrand. Here's what we're taking the integral of, okay? And it makes sense for us to say that u is 3x plus 4. And we know immediately then that will give us the integral of u to the 12th dx. Now, we don't have any extra stuff here except dx, but we can't have a variable u and a variable x in the same integral. So we've got to still replace dx. Now, remember what I said over here, this is kind of our workspace to get the relationship between du and dx. And remember what we talked about a moment ago, that we'll figure out that du is really the derivative of u times dx. And in this case, the derivative of 3x plus 4 is just 3, and so it's 3 times dx. Now, this is the reason this problem doesn't work out so neatly as the last ones. Previously, I've been able to do a direct replacement for du because I had exactly on the right side what was left over in the integral. But in this case, I don't. Now, here's the way we go about thinking this through. I need to replace dx. So I look at this with stuff about du. See, with stuff about du. So I look at this equation and I find the dx stuff. So all I need to do is solve this equation for dx. Now I know normally we divide out constants, don't we? But in this case, it's really better to do something like multiply by a reciprocal. So what I'm going to do is I'm going to multiply by 1/3 on this side, and when I multiply by 1/3 on the right side, I end up with just dx. And so now I have the value of dx, and every time I see a dx, I can replace it with 1/3 du. So that allows me to go to this integral, and in place of dx, I'm going to put a 1/3 times du. Now I'm going to do a couple more steps. I'm going to rearrange this so I have that constant factor of 1/3 in front. And then I suppose really what I could do next is that factor of 1/3 is a constant. So I can take it outside the integral altogether, can't I? Now, I can easily integrate u to the 12th with respect to u, and that's what I've been trying to get to all along, hasn't it? So I've got my 1/3 out here. To integrate u to the 12th, I increase the exponent by 1, and in front of that, I have to offset by the reciprocal of that exponent, don't I? So that would be 1/13, 1/13, plus our constant of integration. And of course, then this ends up being 1/3 times 1/13 is 1/39, isn't it? And u is really 3x plus 4, okay? And that's raised to the 13th power here, plus our constant. And so here is the resulting integral. And like I said, it doesn't always work out so nicely as it did in this case. And in this case, it didn't work out so nicely as it has in the previous cases. But we can still accomplish it. Now let's get ready for the, well, in fact, let me write down the next example. I believe we're beginning to gain some momentum here. When we look at this problem, I bet we can immediately think that we're going to make a substitution of u being 2x to the 4th plus 7. That's what I can imagine that we might think. Now, well, let's go ahead and start the problem. So we'll rewrite it. The integral of 5x cubed times 2x to the 4th plus 7 raised to the 8th power with respect to x. Now, this is different in several ways, or particularly in one way. And you're right, the substitution I'm going to make is I'm going to replace the inside the parentheses, what's inside the parentheses, with a u. Now, keeping that in mind, then immediately we can figure out that du is what? It's the derivative of 2x to the 4th plus 7 times a dx. So in this case, that would be what? 8x cubed times a dx. Now, I want you to pay particular attention here, and this has happened in each of these cases, that sometimes we had du match exact, well, let's get started here by making that substitution. Okay, so this is what our problem looks like after that substitution. Now, it's important to recognize that our substitution probably is a good choice if our derivative has a power of x that matches what's left over. See this x cubed? See this x cubed? Because the whole issue is that we are going to have an x cubed dx to make a replacement. See, we've got an x cubed and we've got a dx, and that's going to have to play into the replacement for a du. But before we go further here, my suggestion is let's take that factor of 5 that is a constant factor, and let's just move it out of the way so we don't have to worry about it. That is, we'll factor it outside the integral sign, and then inside we'll rearrange so we have the x's all together at the end. So don't you agree that's exactly what we had previously? Now, we come over and we look at what our du is. And actually what we're doing is we're saying we need to replace this stuff with u things. Okay? This x cubed dx we need to replace with u things. And so to do that, we look over here at our little formula. See, we look right here at our formula, and here is x cubed dx. So if we could solve this equation for x cubed dx, and we could do that by multiplying both sides by 1/8, then we would be able to replace x cubed dx with 1/8 du. And so that's what we do right here. We replace it with 1/8 du. Now, once again, we have a constant factor of 1/8. This is just u to the 8th times 1/8 du. And that constant factor of 1/8, we'll go ahead and factor it out also from the integral. See, we're bringing it all the way out. And so our integral ends up just being the integral of u to the 8th du. So in front we have a 5/8. And when we integrate u to the 8th, we have to increase the exponent by 1 and multiply by the reciprocal of that new exponent, and don't forget our constant of integration. And now it's a matter of resubstituting and multiplying out. Well, 5/8 times 1/9 is 5/72, isn't it? And of course, u to the 9th power is nothing more than 2x to the 4th plus 7 raised to the 9th power, plus our constant of integration. And we could check this, but I'm pretty sure that we're absolutely correct here. Well, I think from this introduction, I want to give a lot more problems, but I don't want to make this particular video so long that it takes too long to go through. So I'm going to stop this one, and then we'll start up with the second part.